All right, we're going to take a look at what's called the common ion effect. So this is your notes on the front, and you got a few practice problems on the back. So the common ion effect occurs when a reaction or solution that's at equilibrium has a chemical added to it with an ion that is common to one that's already present in that solution. This addition of an ion shifts the equilibrium, as predicted by Le Chatelier's principle, to return the reaction or solution to equilibrium. So we're adding something that's already there, and we're shifting the equilibrium. So we're still going to use the methods previously learned in this unit, such as equilibrium expressions and Rice tables, to determine the effect of the common ion on our equilibrium. So we're going to take a look at a couple examples on how this works. All right, we're going to take a look at an example here. So a solution is formed by dissolving iron hydroxide, FeOH2, in water to create the equilibrium below. And we can see that reaction given there. When 0.010 molar sodium hydroxide is added, or then that much sodium hydroxide is added to the reaction. So we establish an equilibrium, then we add another chemical to that, and we disrupt that equilibrium. So we want to know the concentration of each ion at the new equilibrium. So each ion meaning the iron and hydroxide. So first thing, when we add this NaOH, we're really adding sodium ion and hydroxide ion. So our amount of hydroxide is the one that's changing because that's the one that is in common between our sodium hydroxide and our iron hydroxide. That is our common ion. So we've established an equilibrium and we're adding more hydroxide, and we want to see how does that shift our equilibrium. So we're going to use a Rice table for this since we're trying to figure out new concentrations at equilibrium. So first thing is we can cross out that solid because it does not have a concentration. And then we can look at our iron and hydroxide. So initially the chemicals are already at equilibrium, and we can say that they have concentrations of X, because we don't know its initial concentration, and 2X, okay, because of that coefficient of 2, it would be twice as much. And then our change in equilibrium is caused by adding the sodium hydroxide. Now the hydroxide is the key part. So since this is for every 1 sodium hydroxide, we have a 1 hydroxide ion, it would have the same concentration. So what we're adding is 0.010 molar hydroxide ion to the reaction. We're not adding any iron to the reaction. So at equilibrium, we have X amount of iron, and we have 2X plus 0.010 hydroxide. So that gives us our equilibrium. Now, we want to solve for X. To do that, we would need our equilibrium expression. So let's take a look at it. Dealing with solubility, SP. So we'd have our concentration of iron times our concentration of hydroxide squared because of that coefficient of 2. And then we could plug these in. I'm going to wait to plug in my KSP value because we're going to have some things to discuss here. So our amount of iron is X at equilibrium, and our hydroxide is 2X plus 0.010. Now, this part is squared. So if we were to start simplifying the right side of this equation, we would have to square this term, which means that this would turn into a quadratic. And the College Board has decided that doing quadratics in chemistry is not really testing your chemistry knowledge, but more if you can actually do a quadratic formula. So they've eliminated that off the AP test. But we can do that here too. There's a way to simplify this that allows us to get rid of that quadratic. So, and this is why significant figures are our friends here. So our KSP value that we have up here is really, really small. 10 to the negative 16th is a very small value, which means that our iron and our hydroxide, even initially, would be very, very small amounts. That X and that 2X would be very tiny values. So down here, if we had this very small value and we added 0.010 to it, a much larger value, and we rounded to significant figures, this term, 2x plus 0.010, would really just equal that 0.010 when we rounded to our significant figures. So that means we can simplify our equation to x times 0.010 squared. Now let's plug in our KSP value. That's going to equal, if we did 0.010 squared, we get 0.00010, and we're multiplying that by x. So then we can divide by that, and our x value would equal 7.9 times 10 to the negative 12th. So let's just test our little theory up here. If we were to plug in that x value here, multiply it by 2, and then add this, we would still, rounding to significant figures, get this number. So that means that our assumption is good, and it's fine. We can do it. You can even test it in your calculator. So we've got our x value, which means we have our answer. We wanted the concentration of each ion at our new equilibrium. Well, the concentration of iron is just x. So we can write that in. So that would be 7.9 times 10 to the negative 12th molar. And our concentration of hydroxide at equilibrium is 2x plus 0.010. Well, testing in our calculator, we can see that that's just 0.010 molar. Okay, so this is where we get to kind of assume that x is so small that it's not going to affect our calculation here, and it really doesn't. And that's because our KSP value is so small. It has that very tiny, or that very large negative exponent, so it's going to be very, very small decimal, meaning not much of it dissolves. Okay, we're going to try another one of these so you guys can see how this works again. All right, the other thing we can see from that previous example, I didn't have space to put this part on my previous slide, but is that based on the values that we were given, or that we got at equilibrium, and Le Chatelier's principle, we can see that the equilibrium shifts left due to the addition of our common hydroxide ion. So because we added hydroxide, we're going to shift that equilibrium to the left and reduce our amount of iron that we started with. All right, we're going to try the second example here. So for this second example, it says calculate the solubility of calcium fluoride in a solution where 0.010 molar sodium fluoride is added. So we're using that same molarity there, which is fine. The solubility product constant of calcium fluoride is 3.9 times 10 to the negative 11th. So still a pretty small value because that 10 to the negative 11th. We'll see if we are able to make that same assumption. So first, we're going to have to use a Rice table here. We've got calcium fluoride, solid, in equilibrium with calcium ion, and 2 fluoride ions, both being aqueous. First thing, always, we can eliminate that solid. All right, so initially we have some amount of calcium and some amount of fluoride, but fluoride is twice as big as our calcium because that coefficient. Now we are adding NaF. So really we're adding sodium ion and fluoride ion. So our common ion is that anion again, the fluorine. So, and again, it's a 1-to-1 ratio, NaF to just F minus. So we're really adding 0.010 molar fluoride ion, and we're not adding any calcium. So since we're adding a product, we know that this would shift our reaction left and change our equilibrium there. So our amount of calcium at equilibrium would be X, and our amount of fluoride would be 0.010 plus 2x, or 2x plus that, either way. And now we'd want to plug it into our KSP equation. So that would be our calcium ion times our fluoride ion squared. Now we're going to make the same assumption. We are going to say that this is basically equal to 0.010. Reset. 010. And we can do that because our KSP value is so small, and which means that our X value here would be very, very small, meaning when we added these together, we would essentially round it to this number anyway. So our KSP 3.9 times 10 to the negative 11th would equal our calcium concentration, X, times 0.010 squared. We would get 3.9 times 10 to the negative 11th equals 0.00010x, which means X would equal 3.9 times 10 to the negative 7th. As always, you can pause and check those calculations, make sure you're on the right track. So that gives us our X value, and now we can find our concentration of our calcium ion and our fluoride ion at equilibrium. All right, so our calcium ion concentration would be X, which would be 3.9 times 10 to the negative 7th. Our concentration of our fluoride ion would be 0.010 plus 2x, which would end up rounding to 0.010 molarity for both. And we want to know, the question is actually asking, for the solubility of the whole chemical. So that's meaning really what is the concentration of our chemical at equilibrium. Now, the easiest way to do that is to just look at the ratios. So calcium is in a 1-to-1 ratio with calcium fluoride. So that means that our concentration of our chemical together would be 3.9 times 10 to the negative 6 molar calcium fluoride. And that would be our final answer. So there's a couple questions to practice this a little bit. It's not something that comes up a ton, so that's why I didn't do a ton of practice on it, but you should definitely take a look.